Dear students, today we will discuss about the metal-metal bonds, overlapping of d orbitals, pi back bonding and its effects on various properties of molecule, bridge bonding and its types. To introduce d-pi p-pi bonding, I would like to tell you all that though the p-pi bonding is important for the second period elements, it is of little importance for heavier elements, which give multiple bonds through the use of d orbitals. Thus, the bond order of 1.8 in the sulfate ion having no vacant p orbitals indicates 80% pi bonding due to the overlap of filled pz orbitals on an oxygen atom with the vacant low energy dxz orbital on sulfur atom. The d-pi p-pi bonding is more favorable as the d orbitals project into the general direction of the bond formations a better overlap than the purely side overlap of p-p orbitals. The extent of the double bond formation increases in the series phosphate less than sulfate less than chlorate as the formal charge on the central atom increases. Oxyanion of fluorine is not stable as positive charge cannot reside on fluorine atom due to its high electronegativity, and the absence of any low energy orbitals rules out the possibility for the double bond formation. The general classes of metal-metal bonding are covalent bonding. It is the most common type of metal-metal bonding. In this bond, one electron is counted from each metal center. Dative bonding. In this type of bonding, one metal makes use of filled d orbital, that is lone pair, to coordinate to an empty orbital of the other metal. In most of the situations, dative bonds are counted as covalent bonds. Symmetry bonding. This type of bonding is not common as it is a weak metal-metal interaction caused by molecular orbital symmetry. Interactions of filled and empty metal-metal bonding and or anti-bonding orbitals. This type of bonding is found in metals having d8 configuration. To understand about overlapping of d orbitals, the overlapping of d orbitals makes different types of metal-metal covalent bonds. The figure shows the types of covalent interaction from strongest to weakest, as we can see in this figure. Now this figure shows overlapping of d orbitals. Overlap of two dz square orbitals form a sigma bond, which is stronger than the pi bond formed by overlap of two dyz or dxz orbitals. Overlapping of dx square y square orbitals is not shown as it results in ml bond formation. Molecular orbital diagram for the interaction of two square planar metal centers is shown in this figure. As you can see, it has molecular orbitals sigma, pi, delta, delta star, pi star and sigma star. Sigma, pi and delta are bonding molecular orbitals, and delta star, pi star and sigma star are anti-bonding molecular orbitals, which are obviously higher in energy than bonding molecular orbitals. Initially, electron fills the bonding orbitals, but if more than 8 electrons are added, metal-metal bonds starts cancelling and anti-bonding orbitals begin to form. The energy of anti-bonding orbitals is higher than the bonding orbitals. Therefore, anti-bonding orbitals are less stable. The table that I am showing you, it shows the bonding between two square planar metals. The metals having different geometry may have different bond orders. As you can see, D1 overlap shows a single bond, D2 overlap a double bond, D3 overlap a triple bond, D5 overlap triple bond, D6 overlap double bond, D7 overlap single bond, D8, D8 overlap, no bond. D4, D4 is the optimum case as it results in the formation of quadruple bond. Here are some examples of multiple covalent bonds in this figure. You can see all these show multiple covalent bonds. Now we will study about pi back donation or pi back bonding. When an electron is moved from an atomic orbital of an atom to a pi star antibonding orbital of a pi acceptor ligand, this is known as pi back donation or pi back bonding. It is found in the transition metals which multi-atomic ligands such as ethylene, carbon monoxide and nitrosonium show. In this process, the metal having excess of negative charge is used to bind the ligand. Complexes such as nickel tetracarbonyl and G's salt exhibit back bonding. It involves a synergic process in which the electrons from the filled pi orbitals or lone pair of the ligand are donated into an empty orbital of the metal, and at the same time back donation of electrons take place from the ND orbital of the metal to the empty pi star antibonding orbital of the ligand. Types of back bonding, if we have to explain, then it is of two types: central atom to side atom and side atom to central atom. If central atom has lone pair of electrons or filled pi orbitals and side atoms have vacant orbitals, then central to side back bonding takes place. For example, in nitrogen SiH3 thrice, where lone pair on nitrogen atom are involved in back bonding with empty orbitals of silicon. Opposite is the case in side to central atom back bonding. For example, in BF3, where electrons from filled pi orbitals of fluorine are involved in back bonding with empty orbitals of boron atom. Both these cases, as you can see in this figure, are described first for BF3 and then for nitrogen SiH3 thrice. Now back bonding can take place in three ways, that is overlapping of 2p pi metal ligand, 2p pi 3p pi metal ligand and 3p pi 2p pi metal ligand orbitals. Since in 2p pi overlapping, the energy and symmetry of orbitals of both metal and ligands are same, therefore effective overlapping will take place. Hence, the 2p pi back bonding is highly stable. Therefore, with respect to effective overlapping of the orbitals, the order of stability of back bonding is 2p pi greater than 2p pi 3p pi greater than 3p pi 2p pi. Note that 3p pi back bonding is not possible, as if metal and ligand both are from third period, the size of both the atoms will be very large and effective overlapping will not take place. Conditions of back bonding, if we have to discuss, they are: metal atom should have vacant orbitals, ligand should have lone pair of electrons or filled pi orbital, at least one of the atoms should be from second period, and if both are from third period, then effective overlapping will not take place. Now we will study about effects of back bonding. Bond length of the molecule always decreases whether the back bonding is from central atom to side atom or from side atom to central atom, as due to back bonding, partial double bond character is induced in the molecule, as a result of which bond order increases and hence bond length decreases. This is the reason for short BF bond length in boron fluoride as compared to BF4 minus ion. This is very clearly understood in this figure. We will now discuss the effects on hybridization, shape and bond angle. Taking an example of BF3 molecule, here lone pair on fluorine atom is donated to vacant pi orbital of boron and results in side to central atom back bonding. In this, the hybridization of molecule will not change and it remains sp2 hybridized. Also, the shape of the molecule remains trigonal planar. This is clearly understood in this figure. But in nitrogen SiH3 thrice, as lone pair on nitrogen atom is donated to empty orbital of the silicon and central to side atom back bonding takes place, the lone pair on nitrogen atom is no more in hybridization and hence the hybridization of the molecule changes from sp3 to sp2, that is percentage S character increases and hence the geometry of the molecule also changes from pyramidal to trigonal planar. Now, as the geometry of the molecule changes by change in hybridization, bond angle of the molecule also changes. This figure shows that lone pair of electrons is back donated and then we have square planar shape. Next is the effect on Lewis acidic and Lewis basic character. Back bonding is nothing but intramolecular Lewis acid base interaction. For example, on comparing the Lewis acidic character of BF3 and BH3 molecule, the Lewis acidic character of BF3 is less than that of BH3 because it undergoes back bonding, due to which the pi orbital of the boron atom is no longer vacant and hence BF3 cannot act as a Lewis acid. This is clearly understood in this figure. Similarly, in the case of nitrogen SiH3 thrice, the lone pair of electron on nitrogen atom is involved in back bonding with vacant pi orbitals of silicon atom. They are no longer available for further donation and hence nitrogen SiH3 thrice is less basic than nitrogen CH3 thrice, which do not involve in back bonding as carbon atom do not have vacant pi orbitals. You can see this clearly in this figure. This is the reason of better Lewis basic character of ethers than that of SiH3 twice oxygen. This is clearly understood in this figure. Next we study about adduct formation. Either the lone pair or the vacant pi orbital of the molecules are involved in back bonding. In both the cases, the efficiency of bond formation decreases. This is the reason for poor adduct of SiH3 twice O and BF3 as both are involved in back bonding. This is clearly understood in this figure. Similarly, NH3 and BBr3 forms good adducts because none of them are involved in back bonding. Therefore, we can say that the molecules which are better Lewis base can form better adducts, as is understood in this figure. To study back bonding in borazine, which is also known as inorganic benzene because its structure is similar to that of benzene. In borazine, nitrogen and boron are bonded as a 6-membered ring or has 6 pi electron system similar to that of benzene. But as compared to benzene, borazine is kinetically less stable and thermodynamically more stable. This is due to back bonding between boron and nitrogen atoms, which induced polarity within the molecule, and the bond between nitrogen and boron become ionic. This is the structure of borazine shown here. Now in borazine, although nitrogen is more electronegative than boron, but due to back bonding there will be a partial negative charge on boron and partial positive charge on nitrogen. Nitrogen has lone pair of electron which are back bonded with vacant pi orbital of boron. For example, if borazine is going to react with HCl, reaction will take place. Here, borazine adds the 3 HCl molecules. Bridge bonding. Bridge bonding is another type of back bonding. It causes polarization in the molecule having vacant orbitals as they participate in hybridization, due to which hybridization always increases to one step, that is sp and sp2 and sp2 and sp3, and percentage S character decreases. There are two types of bridge bonding, 3-centered 2-electron and 3-centered 4-electron bridge bonding. Bridge bonding is only possible if there is no back bonding and no steric crowding within the molecule. BH3 involves in bridge bonding and extra sigma bond is formed with another BH3 molecule. Here, the shared pair electrons of boron and hydrogen atom are donated to the vacant pi orbital of the next boron atom. In this way, 2 electrons are shared between 3 atoms, that is 3-centered 2-electron bridge. Bonding will take place, which is shown in this figure. This is the resultant B2H6 molecule. The bridge bond of B2H6 is also known as banana bond, as the shape of bond is similar to that of banana. This is because of the hybridization, that is sp3s sp3 of boron hydrogen boron atom involved in bridge bonding. On the other hand, AlCH3 thrice molecule also involved in bridge bonding, in which 2 sigma bonds are formed between 2 molecules of AlCH3 thrice. Here, 4 electrons from 2 of the AlC bond are shared between 3 atoms and results in 3-centered 4 electrons bridge bonding. The resultant Al2CH3 molecule is shown. Here, the hybridization of Al-C-Al bridge bond is sp3, sp3, sp3. To understand the chemistry of molecules involved in bridge bonding, we will take an example of B2H6 molecule. This figure shows B2H6 molecule where different H are denoted by different symbols, like HT are the terminal ones and HB are the bridge ones. Here in the molecule there are two types of bonds, that is bridge bonds and terminal bonds. Bridge bonds are stronger and longer than that of terminal bonds because of some reasons. The reasons are: the formation of bridge bonds results in the formation of a 4-membered ring, and in order to stabilize the ring structure, the bridge bonds are longer than that of terminal bonds. Also, the bridge bonds are stronger because there are 2 electrons shared between 3 atoms, and hence force by which electrons are held within the bond is more. This can be explained by considering methylation of B2H6. As it takes place on terminal bonds instead of bridge bond, product is formed. You can see the methylation taking place on terminal bonds in this figure. Let us now understand the cleavage of bridge bonding. There are two types of cleavage possible in molecules, that is homolytic cleavage and heterolytic cleavage. In homolytic cleavage, 2 electrons in a cleaved bond are divided equally between the products, and in heterolytic cleavage, the bond break in such a way that the shared pair of electrons remain with one of the fragments. Taking an example of B2H6, bulkier bases such as NCH3 thrice result in homolytic cleavage and form 2 molecules of BH3 molecule, because the bulky groups, that is CH3, cause steric crowding. Therefore, NCH3 thrice cannot attack on boron having more number of terminal hydrogen. This is clearly understood in this figure, which shows homolytic cleavage. On the other hand, lighter base such as ammonia causes heterolytic cleavage and results in the formation of BH2 plus and BH4 minus as shown in this figure. So, dear students, if I have to summarize the whole thing, I would like to tell you these points. The overlapping of d orbitals makes different types of metal-metal covalent bonds. This we have clearly understood. Then, overlap of two dz² orbitals form a sigma bond, which is stronger than the pi bond formed by overlap of two dyz or dxz orbitals. The energy of antibonding orbitals is higher than the bonding orbitals in a molecular orbital. Therefore, antibonding orbitals are less stable. Back bonding involves a synergic process in which the electrons from the filled pi orbitals or lone pair of the ligand are donated into an empty orbital of the metal, and at the same time back donation of electrons takes place from the Nd orbital of the metal to the empty pi star antibonding orbital of the ligand. Back bonding is basically of two types, that is central atom to side atom and side atom to central atom. We also studied that back bonding can affect bond length, hybridization, shape and bond angle, Lewis acidic and basic characters, and adduct formation. Bridge bonding is another type of back bonding. It causes polarization in the molecule having vacant orbitals as they participate in hybridization. It is of two types, 3-centered 2-electron and 3-centered 4-electron bridge bonding. Bridge bonding is only possible if there is no back bonding and no steric crowding within the molecule.